Hey everybody, Dr. A here, and in this video we're going to be exploring another example dealing with axial loads. So let's take a look at what we're given here. Here we're being told to use the method of sections to compute the normal force at point B. So method of sections, what is that? Well, that's a technique that we've learned in statics that deals with making a cut section at a particular spot in a member and then determining what the internal loads are at that spot, okay? And in this particular example, the spot we're interested in is point B. So I'm gonna say solution, and I'm gonna say use method of sections, which I'm gonna abbreviate MOS, to make a cut at point B. Now, when we do that, we use method of sections, we isolate one side or the other of that member. So when I make this cut at point B, I'm either going to look at everything to the left of point B or everything to the right at point B. Now notice that if I look at everything to the right of point B, that's going to include this fixed connection, all right? Doesn't matter which side I look at. Is it going to make a difference if I look at the left side of point B or the right side of point B? No, it's not, because this whole member is in static equilibrium. Additionally, each part of it, if you segment out each part of it, it will also be in static equilibrium. Every single part of this thing will be in static equilibrium. So I could look at a left free body diagram or a right free body diagram when I use that method of sections. But again, if you look at a right free body diagram, you have to remember to solve for those external forces at point C first, because that is in the right free body diagram, okay? So let's go ahead and do this, all right? Let's consider a left free body diagram, okay? So when I do that, I'm going to have my member here, and I've made my cut here. And I have my uniformly distributed axial load here. That's 3 kilonewtons per meter. And that is spread out over how many meters? Well, this is 2 meters because I've made the cut at point B, right? Here's the cut right at point B. So what becomes visible here? Well, I'm going to have a normal force at point B, and I'm going to have a shear force. Let me back this up a little bit. I'm going to have a shear force at point B, and I'm going to have a bending moment at point B. Now, if you've watched my previous videos, this is an axially loaded system. So really, all we need to worry about is the loads along the longitudinal axis of the member, which for internal loads, that's NB. VB is a transverse load, that's a shear force, and MB is a bending moment, both of which are 0 because all you have, the only applied loads you have are along the longitudinal axis, which means you're only going to engage in B here. So I'm going to say sum of the forces along the longitudinal axis equals 0, which really means sum of the forces in the x direction equals 0 for this particular problem. Now, when I have sum of the forces in the x direction, what's going to show up here? I'm going to have negative 3 kilonewtons per meter times 2 meters. Plus NB equals 0. That's everything in the x direction. I do some rearranging, and I'm going to get NB is equal to 6 kilonewtons pointing to the right, which is also 6 kilonewtons in tension. Okay? So that is my final answer. Now, let me ask you another question that I've already asked. Could I have analyzed a right free body diagram here? The answer is absolutely yes. Okay, I could have done that. I could have said consider a right free body diagram. Okay, would I have gotten the same answer for NB? Would I have also gotten 6 kilonewtons in tension? Absolutely. Okay, absolutely. So my task to you is, why don't you try that on your own? I'm not going to do it in the video. Why don't you do it on your own and double check yourself. Use a right free body diagram, but remember first, you have to get CX first, okay? And when you make this cut at B, you look at NB coming out of the cut at B and solve for NB using some of the forces in the X direction, but using a right free body diagram with CX as part of that. Okay, so I challenge you to do that on your own. You should get 6 kilonewtons in tension as well, but your 6 kilonewtons will be pointing to the left. Okay, so if you use a right free body diagram, I'll make a note here for you. By using a right free body diagram, NB should be 6 kilonewtons pointing to the left, which is still 6 kilonewtons in tension. Why is that? Well, it's because at point B, you have 6 kilonewtons in tension, but if you look at one side of it, it'll be pointing to the left. If you look at the other side of the cut, it'll be pointing to the right because point B is in static equilibrium. So looking at it from the two different perspectives of the two different free body diagrams will point in the opposite direction, but it will still mean the same thing, 6 kilonewtons in tension. So I challenge you to do that on your own and come to the same conclusion. If you found this video helpful, please hit like and subscribe and be on the lookout for other content like this. Thanks for watching.